and b over exact equations, and then all those substitution methods. Okay, so I'll go through all these. I personally think this was your hardest exam, but you know, whatever, we'll get through it. Okay, so starting with 2.1a, let me go ahead and so all from A, so all from B. Okay, so with 2.1a, let's go ahead and identify our m and our n. So our m of xy here is just our x, because remember your m goes with your dx, and then our m of xy is that whole phrase, x squared y plus 4y. Okay, so now we are going to take the partial derivative of m with respect to y, because it went with the dx. So when you do that, that is equal to 0, because keep in mind you're taking it with respect to y and holding x constant. So if x is a constant, the first derivative of a constant is 0. So now we're going to take the partial of n with respect to x, because it went with the dy. Okay, and when we do that, we're taking it with respect to x. So we do it like normal, so we get our 2xy, and then this 4y is a constant, so it goes away. Okay, so obviously you can see here, these are not exact, and we will be converting these into, converting this into an exact equation during this. So let's come up with our integrating factor. Okay, so there are two equations you can use for this, your m of y minus your n of x over n, or your n of x minus your m of y over m. Okay, so when you do the first one, you should get 0 minus 2xy, and then over your x squared y plus 4y. You can factor out a y of that bottom term. So you'll have 2xy negative x squared plus 4 times y. These y's cancel, and you're left with negative 2x over x squared plus 4. Okay, so now let's do the second part where we have our 2xy minus 0, and then divided by our x, which leaves us with 2y. We are trying to solve for an integrating factor, and I know that the 2y looks easier, but keep in mind when you integrate this, you're going to get a natural log, so you don't have to deal with e at all. So I'm going to use this one. You're more than welcome to use this for your integrating factor, but it makes the problem a lot harder. So I wouldn't just do this step. I would actually solve for your integrating factor and see which one is more reasonable before you start actually multiplying everything through. So I'm going to get rid of this, and we're going to, actually, I'll solve for our integrating factor first. So our integrating factor is mu of x, where mu of x equals e raised to the integral of whichever one of these we want, but we have chosen this. So of 2x over x squared plus 4, and that too is still negative. Okay, and when you integrate this, it's just a u sub problem. you will get 1 over x squared plus 4. Okay, and that's really nice because, like I said, this integrates as a natural log, and so we don't have to deal with this e at all. Okay, so now that we have our integrating factor, I'm going to get rid of all this, and we can start actually converting the equation. Okay, so we have our integrating factor, so we're going to multiply it through the whole equation. So what that gives us is x over x squared plus 4 dx, and plus x squared y plus 4y all over x squared plus 4 dy, still equal to 0. Okay, so if you want to check, we can take the partial of these again. They're going to be 0, so if you take the partial of m with respect to y, you get 0 because there are only x terms in that. And then the partial to n with respect to x, you'll also get 0, which is great. Okay, and do keep in mind that this, I probably should have simplified it. That is for dx. This simplifies just to y, because if you factor out a y here, you're left with an x squared plus 4 over x squared plus 4. So you're left with just y dy equals 0. And that's how you can easily see that differentiating over x of a y term is going to give you 0. Okay, so now that we know that these are good, we can start the next step. Okay, so we know that our f of xy is equal to the integral of our n xy dy plus g of x. Okay, so what that is really saying is that our f of xy equals the integral of y dy plus g of x. And again, all of these equations are either from Dr. Norton's sheet or the sheet that I put out earlier. I can release it again. I don't know how much it helped you guys, but it makes me feel better when I have like a step-by-step list to follow. But either way, these equations will be available to you. Okay, so when you integrate that y term, you'll get 1/2 y squared plus g of x. I'm sorry if you keep hearing my door open and close. My dog is very indecisive. Okay, so this is honestly the main part of what we need, but now we have to solve for this g of x. And we know that our g of x equals the integral of m minus the partial with respect to x of the integral of n x y dy, and then this whole thing integrated with respect to x. Okay, and I know that looks really scary, but once you start plugging in the values, it's really not that bad. So we have our g of x is equal to our m equal to the integral of our m, and keep in mind this is the m from your new equation. When you multiply by your integrating factor, you get new m's and n's. So don't plug in the last one from the last step. Of m, and then minus the partial of this, but we just solved for that. So now we have the partial with respect to x of 1/2 y squared integral. Oh, I'm sorry, that is the integral. you have the partial of that, and then the whole thing dx. So lucky for us, this is 0 because the partial with respect to x of something that only has y terms is 0. Okay, so now we have our g of x is just equal to the integral of x over x squared plus 4 dx. Okay, and when you take that integral, you should get another natural log term. So you will get your g of x is equal to 1/2 times the natural log x squared plus 4. Okay, so that's super great, and we're one step closer to being done with this problem. So that is just our g of x. We solved for our f of xy. Actually, I don't want to write it there. I feel like that's confusing. I'll just move it down. Okay, there's our g of x. So our f of xy equals our 1/2 y squared. Don't forget, we already solved for that part of the equation. And don't forget to add it in. This is just the g of x. And then plus our 1/2 the natural log of x squared plus 4. And then this is all equal to c, because we've been ignoring our integrating constants this whole time, and now we are plugging it back in. Okay, and we do have a initial value on this problem, which is, I'm trying to find it, y of 1 equals 1. Okay, so y of 1 equals 1. So we get 1/2 times 1 plus 1/2 times the natural log of 1 squared plus 4 equals c. So we know that our c equals 1/2 plus 1/2 the natural log of 5. Okay, oh, I guess I already have a c, but that's okay. So now we can say that our answer, our final thing, is 1/2 y squared plus 1/2 the natural log of x squared plus 4 equals 1/2 plus 1/2 ln of 5. Okay, so hopefully that makes good sense, and that is the answer to this first problem. So let me try to get rid of all of this, and we can start. Okay, so that was 2.1a, and now we can start on 2.2a. Okay, and we're told to solve it using a substitution. So we have y squared plus xy dx plus x squared dy equals 0. And we're going to use the substitution y equals ux. Okay, so if y equals ux, then dy dx equals the derivative with respect to x of this over here. So using your product rule, you will get du dx times x, and then plus u. You multiply by your dx, and you get dy equals x du plus u dx. And that'll be the same every time, so if you just want to memorize it, that's fine. So we're going to start our substitution. So everywhere you see any of these terms, we're just going to plug in to our original. So our y squared, so we have u times x quantity squared plus x times ux all dx, and then plus our x squared, and then times our dy term, which is x du plus u dx. And it's still equal to 0. I have a bad habit of dropping that, but don't. Okay. So what we can do here is if you distribute this through, you have an x squared on both. So I'm going to factor out an x squared, which leaves us with u squared plus u dx. Okay? Then we can also factor, well, we already have an x squared here. X squared x du plus u dx still equal to 0. Okay, so when you have an x squared on all terms, we can just divide by x squared, and we'll get rid of that entirely. So now we have a u squared plus u dx plus x du plus u dx still equals 0. Okay, so we have a u dx here and a u dx here. So we have a u squared dx plus 2 u dx plus x du all equal to 0. Factor out that dx, u squared plus 2u dx equals our negative x du. And now hopefully it's looking very, very separable. And this, sorry, I'm sorry, this should be a dx here. Okay, so we can just divide like we generally do with our separable equations. 2u here, du equals negative 1 over x dx. Okay, and that is the solution to this problem because it is specified in the instructions. You don't have to solve for the integrals. I know it was bonus the first time you took the test. I don't know if you'll be doing bonus points on the retakes. I know he hasn't really been doing them for all the online testing, so I wouldn't bet your life on it. Okay, so now let's do the next problem. Okay, so 2.3. 2.3 is x squared dy dx minus 2xy equals 3 y to the 4th. Okay, and we're told to solve it using a Bernoulli method. Okay, so to even start with the Bernoulli method, we need to put it into standard form. So we will divide by that first term. So we have dy dx equals negative 2 over xy equals 3y to the 4th divided by x squared. Okay, so now that it's in standard form, we can start with our problem. Okay, so your u in this case, so u equals y raised to the 1 minus n. In this case, our n is 4. Where n is 4 because of over here. So 1 minus 4 gives us our negative 3. We know that our u is y to the negative 3. So we know that du dx is equal to negative 3 y to the negative 4 dy dx. Okay, and we're going to use those substitutions later. Okay, so the next step is we're going to divide all everything. We're going to divide everything by that y to the 4th. So you should get y to the negative 4 dy dx minus 2 over x y to the negative 3 equals your 1 over x squared. Oh, I'm sorry. We'll still have that 3. Okay, so now we're looking pretty good over here with things that we want to substitute, except for I'm going to multiply the whole equation by 3 so I can make a direct substitution right here. Okay, so 3, make this a 6, and then this becomes a 9. Okay, so now I can make direct substitutions. So I have my 3y to the negative 4th dy dx, so that's du dx. Okay, and then our y to the negative 3 is just our u, so minus our u equals our 9 over x squared, and this is negative. Okay, and that's really it. That's all you had to do. It's now in its integrable form. So get rid of this. Okay, so 2.4 is the last one on exam A, and that is dp dt equals secant t plus b minus 1 minus 1. Okay, so we're using that substitution with the ax squared plus bx plus c equals u. And so our u in this case is our t plus b minus 1. Okay, so that means our du dt equals 1 plus dp dt. Okay, so all I did was I took the derivative of all these terms with respect to t. Okay, and now we can start substituting. So this also means that du dt minus 1 equals our dp dt. Okay, so now we can directly substitute. So we get du dt minus 1 equals our secant of u minus 1. These minus 1s go away. So your du dt equals your secant of u. And to put this in its completely integrable form, whatever we're going to Divide by this secant to get it over here with our du. When you divide by a secant, it becomes a cosine du and then dt. Okay, and that is how you do that type of problem. Get rid of these. Okay, so 2.1b. Okay, first thing we're going to do is we're going to identify our m of xy and our n of xy. Okay, so our m of xy in this case is our 6xy, and our n is our 9x squared plus 4y. Okay, so we're going to take the partial of m with respect to y. So when we do that, we get 6x, because again, this is like a constant, and we have one y term. Okay, now we're going to take the partial of n with respect to x. And when we do that, we get 18x, and our constant here goes away. Okay, so obviously you can see that these are not exact, so let's start solving for our integrating factor. Okay, so if we use that first equation, we get 6x minus 18x, and then all divided by 9x squared plus 4y. And unfortunately, this does not turn into anything prettier than it is, so let's not use that one. Okay, so when we use the other equation, we get 18x minus 6x divided by 6xy, which leaves us with 12x over 6xy, or 2 over y. Okay, and as you can see, this will integrate as a natural logarithm. Very nice. It's a very nice thing to choose for our integrating factor because we don't have to deal with any nasty exponentials. Okay, so now solving for our integrating factor, our mu of x equals e times the integral of 2 over y dy. So you get mu equals e to the natural log of y squared. Your e and your natural log go away. You left with y squared as your integrating factor. So now we're going to multiply through the whole equation to get a new m and a new n that we can solve with. Okay, so we get 6x y cubed plus 9x squared y squared plus 4y cubed. And then here we have our dx, and here is our dy. Still equal to 0. Okay, so now we have a new m and a new n, and we can start solving for our f of xy. So our f of xy is equal to the integral of m dx plus gy. Okay, so that goes to the integral of 6x y cubed dx plus our g of y. Okay, so the integral of our 6x y cubed with respect to x is going to give us xy equals 3x squared y cubed. Okay, and then still plus our g of y. So now the rest of the problem, we're just going to be solving for our g of y. So we know our g of y equals the integral of our n minus the partial with respect to y of the integral of our n term y, and the whole thing being integrated over dx. Okay, so plugging in all our values, we get our n is 9x squared y squared, and then plus our 4y cubed, and then minus our integral here, which we've already taken, and then we're going to take the partial with respect to y. So the partial with respect to y of this is going to give us minus 9x squared y squared. Okay, and then this whole thing is still being integrated over x. Okay, so these go away, and you're left with, I'm sorry, you're left with the integral of gy, which is 4y cubed dy. I'm sorry, this should be a dy here. Okay, so when you take that, you will get y to the fourth as your gy, so you can finally plug that back in. So you get your f of xy equals 3x squared y cubed plus y to the fourth, and then still equals our constant c at the end, solving for our initial value of y of 1 equals 1, I believe. I'm actually going to scroll back up and look. Yes, okay. Y of 1 equals 1. We get 3 times 1 times 1 plus 1 equals 4, and both equals c. Okay, so plugging that back in, we get our f of xy equals 3x squared y cubed plus y to the fourth equals 4. Okay, and that is 2.1b. So I will get rid of this and we can start on the rest of the problems. Sure. Are you talking to me, Mom? Yeah, I have the dog. Okay, bye. Okay, so we can start on 2.2b, which gives us our y as the square root of x squared minus y squared x plus x dy equals 0. Okay, and we're going to solve that using the same substitution we used for the last one. So our y equals ux. So our dy equals equals u dx plus x du. Okay, so we can start the substitution. Also, I believe Dr. Noring said something about proving homogeneity, which if you guys need help with, let me know. But for sake of time and space, I am just going to start the problem and assume that it's homogeneous. Okay, so doing a substitution here, we get our u of x plus the square root of x squared minus our u of x squared dx plus x dy. Okay, so we have our u of x here. You can see you can pull an x squared out of both of these terms. So you'll get x squared times 1 minus u dx plus x dy equals 0. You have u of x, your x squared can come out, plus x times the square root of 1 minus u dx plus x dy equals 0. Okay. Now we can factor an x out of here. So we have x u plus square root of 1 minus u dx plus x dy equals 0. Okay, and now we can substitute our dy here, which I forgot to do in the beginning, but that's okay because it's not too late. Our x, and then our dy is u dx plus x du. Okay, so these x's can go away. Okay, so we have these two dx's here, so we have 2u dx plus square root of 1 minus u dx, well, I was going to be dx plus x du. Okay, and now we can start separating. Okay, so again, we can factor out that dx, 2u plus 1 minus u dx equals our negative x du, which is going to give us our negative 1 over x dx equals 1 over 2u plus the square root of 1 minus u du. Okay? Oh, I'm sorry, this u is squared. I lost that somewhere. But anyway, yeah, so that is that problem, and we can go ahead and do the last two for this test. Okay, so we can start on 2.3, which we're solving using a Bernoulli method. Okay, so we have x dy dx plus y equals x squared y to the 1/2. Okay, so here in this case, our n is our 1/2, meaning our u equals 1 minus 1/2. So u equals y to the 1/2, meaning that du dx, yeah, I was making sure it wasn't t for this problem. Du dx is going to equal 1/2 y to the negative 1/2 dy dx. Okay, so now we are going to put this into standard form. So our dy dx plus y over x equals y to the 1/2. Okay, so now I'm going to divide everything by our y to the 1/2. I'm going to get y to the negative 1/2 dy dx plus y to the positive 1/2 here because we already had a y, still divided by x, and then equals our x here. I'm sorry, this was an x squared to begin with, so our x carries through. Okay, and now so we can make a direct substitution for this term here, I'm going to multiply everything by 1/2. Okay, so we can now directly substitute that. We have our du dx plus 1/2 x times RU, which is just y to the 1/2, and then equals 1/2 x. Okay, and that is the Bernoulli transformation of this. Woohoo! Okay, we can start on the next one. Okay, 2.4 is the last one for this set. So dq dt equals cosine squared t plus q minus 1. Okay, so our substitution here is our t plus q, which means our du dt equals 1 plus dq dt. Okay, also means our du dt minus 1 equals dq dt. We can substitute here, so we have our du dt minus 1 equals our cosine squared of u minus 1. Our minus 1's go away, so we have du dt equals cosine squared of u, and to get it into its ready to integrate form, we're going to divide by this cosine. Again, dividing by a cosine results in a secant. So you get your secant squared u du equals dt, and that is the ready to integrate form of this. And that is the end of all the practice problems for exam 2. And let me know if you have any questions.